Welcome to Rise Learning Machines seminars. Today I have the honor to introduce Jake Zwart from US Geological Survey. Jake has a PhD from University of Notre Dame. He has a postdoc from US National Science Foundation, and he's now a data scientist at USGS. He's working on short-term forecasts of stream temperature at regional scale and injecting scientific knowledge into machine learning models, and also incorporating real-time observations for near-term water quality forecasts. That's a mouthful for me. Today's topic is stream temperature forecasts using process-guided deep learning. So with that said, I will hand over the screen and the word to you, Jake.
Yeah, so my name is Jake Zwart. I use he, him pronouns. I'm in the data science branch of the US Geological Survey. And I'm going to, in this presentation today, I'm going to split it into two different sections. The first section is going to be talking about some of our work that our group has been doing for injecting process guidance into deep learning models for environmental prediction. And then the later half of the talk, I'll present on an application of process-guided deep learning models. And that's for producing stream temperature forecasts in the Delaware River Basin, which is along the east coast of the United States. And that's in support of some water management decisions. So to start off, to make accurate predictions of environmental conditions using deep learning, we need data. And luckily, there are many observations of environmental conditions, namely stream temperature in the Delaware River Basin. But there aren't observations everywhere and all the time. This image on the left shows locations of stream temperature observations per stream segment over the entire period of record that we're interested in. So from 1960s to about present day. And the chart on the right shows the number of stream temperature observations in this stream network per year per reach, with the lighter yellow colored, meaning that there's more daily values per reach. And you can see that in the northern part of the stream network, there's generally more observations. But there's a lot of gaps along the stream network, and our group has been injecting process knowledge into deep learning models to, extract the most data from, or extract the most information from these data as possible. So how do we do that? So, this is kind of a generic description of a deep learning model. You have input layer, hidden layers, output layer, and then some training data that you want to train your deep learning model with. And scientific knowledge can be designed into deep learning models at many points in the model structure and along the model development process. So we call this process-guided deep learning. So the process-guided part is going to be in purple, deep learning part will be in orange. So any model permits, in fact, kind of require design injection at the point of selecting and preparing input variables. You can do this either through, expert knowledge, what input variables to use, or some feature selection and engineering. You can also use process-based model outputs as input to a deep learning model. You can also use process-based model outputs to help train the deep learning model, using it as a pseudo training observation. Or there's also techniques for modeling the residuals of process-based model. You can also inject process guidance into including process-relevant loss functions. So, for example, you can penalize a model for violating some laws of conservation of energy, for example. And you can also have process-relevant architecture constraints within the model structure itself. And our group is kind of focused on these three different areas of injecting process-guided deep learning for lake and stream temperature specifically. So focusing on structural constraints, also process-relevant loss functions to help guide the model. And then also big component is pre-training the deep learning models on this process-based model outputs. And in the next few slides, I'll kind of go into more detail about these three different components. So for injecting structural awareness, both of time and space for lake and stream temperature prediction, we rely on existing deep learning model structures to help us there. So structural awareness for time, we're using recurrent neural networks which are very useful for modeling time series of water quality, quantity, community composition, etc., because they model whole sequences of inputs and outputs using the same set of parameters for each transition between time steps. There's variants of these recurrent neural networks, such as the long short-term memory network or gated recurrent units that transfer more detailed information among time steps. This enables memory of recent or more distant past events and cumulative ecosystem statuses. So this can be important for predicting stream flow, for example, because some of these cell states can represent like snowpack depth, for example. For spatial structural awareness, we've also been using graph convolutional neural networks in addition to long short-term memory networks to represent spatial relationships in stream networks. We're not using it for predicting lake temperature right now, but for stream networks, it's quite important. This is just an example of how we're representing the structural awareness of the stream network in the deep learning model. So we have a river network, simple diagram here with 4 different segments. We can use an adjacency matrix, so telling the model how these networks or how these segments are related to each other. And we have some direction of flow along the stream network. And so output from one segment can be used as input from another segment using this adjacency matrix. Another component that we're using is this custom loss functions to help guide the deep learning models towards more realistic predictions. An example for predicting lake temperatures that we've been doing is we penalize the model when it violates the law of conservation of energy. So the model cannot magically produce or get rid of energy from one time step to the next. It has to abide by the law of conservation of energy. And so this helps, guide the model towards more realistic predictions that we would expect in the real world. We can also do this for stream networks, telling it or penalizing it when it violates the law of conservation of energy. And we do this through this LSTM plus GCNN and modeling both temperature and flow. And so the stream segments cannot create energy or destroy energy from one time step to the next. Then finally, this last component that we've been using, which is the pre-training on process-based model outputs. We've relied heavily on this for both predicting lake temperature and stream temperature. And it helps guide the model towards more accurate predictions, especially in poorly observed areas. So when we don't have a lot of observations of temperature. In the process-based model encodes equations representing energy and mass fluxes for the environmental system. So translating meteorological drivers into stream or lake temperature. And given the necessary input features, we can make predictions with this process-based model for stream or lake temperatures anywhere. And then we can use this output to train the deep learning models in anywhere that the process-based model can make predictions. So once we've kind of used a deep learning model to emulate this process-based model, we can then fine-tune the pre-trained deep learning model on observations that are available. And this is, greatly improved the prediction accuracy in even data sparse locations.
Question?
Yes.
So when you go to the data driven or when you train it on real data, do you retain the process guiding during that training, or is it 2 separate steps?
Yeah, we retain the process guidance during both steps. So if we have a custom loss function or some sort of structural process guidance, that's included in both the pre-training step, and then those weights are saved and used to initialize the fine-tuning phase. And the same custom loss function, structural awareness, is used in the fine-tuning phase as well.
Thank you.
Yep, thanks. Okay, so those are the 3 different components that we've been using. And then the following is going to be an example of how we've been applying this process-guided deep learning model for predicting lake temperature. So in this example, we've trained 3 different types of models. So a process-based model, which is represented by the green line, a pure deep learning model, which is a LSTM that's represented by the orange line, and a process-guided deep learning model, which would be in purple, which is not yet on the screen. And we train these 3 different models under a variety of data sparsity conditions, ranging from training the models just on 2 observations of lake temperature all the way up to 980 days of observations of lake temperature. And then we evaluated their model performance using the root mean squared error as our test accuracy. And on this graph, we flipped the axis, the y-axis here. So a lower root mean squared error is higher on the axis, meaning more accurate model, and a higher RMSE or less accurate is lower on the axis. And we can see that in data sparse conditions, so at like 2 temperature observations of training, the process-based model does a decent job and actually outperforms the deep learning model, which is maybe not surprising because it doesn't have very many observations. And actually, we don't even show the test performance for the deep learning model because it was so poor. But you can see as we give the models more and more data, the deep learning model starts to outperform the process-based model. And the process-based model actually has some diminishing returns the more data that you train the model with. But our process-guided deep learning model has custom loss functions, a structural awareness of time, and then pre-trained on process-based model output. It was superior in performance across all data sparsity conditions. So even with the 2 days of temperature observations, it was still outperforming this process-based model. But this is kind of, the next few slides are a little bit speculative and kind of some questions that our research group has been having. So, we can see like this pattern across the 2 to 980 temperature observations. But what happens when you extrapolate these lines? What happens when you have more data to give these models? So one possibility is that the process-guided deep learning model kind of loses its edge in model performance, provided more data. This would be consistent with what others have suggested, that deep learning models can kind of be the grandmasters to show us what is actually possible for prediction. And it also raises interesting questions. What are suitable ways and circumstances for which we can use process-guided deep learning models? And our group has kind of proposed that there are 3 different regimes of predictability when it comes to Earth system predictions, and the types of models that are available to us. And so I guess the 3 different regimes are on the far left, where our theory of environmental systems is pretty good and we don't have very much data. And we expect the process-guided deep learning model will be a superior in performance in that case. There's the second regime where we have quite a bit of data, or maybe our theory isn't very good. Process-guided deep learning model is still probably going to be the best, but the deep learning model is starting to learn a lot about the system and can outperform the process-based model. And then this third regime, which we're not actually sure if it exists or not, but it's reasonable to imagine that, for a problem with very limited theory, or maybe nearly infinite and perfect data, a pure deep learning model might be the best available option, rather than getting bogged down in our own theories, which are necessarily simplifications of the real world. But, we think exactly where this dividing line is between the second and third predictability regimes is kind of an open question. Our current process-guided deep learning methods are already quite diverse, has varied strengths and weaknesses to it. And we're only really beginning to scratch the surface and the different ways that we can inject knowledge guidance or scientific guidance into deep learning models. So, for a given problem, a given system, we can imagine like this purple process-guided deep learning curve could follow many different trajectories. And, there might be a bunch of different places where this intersection between deep learning model and process-guided deep learning model curves could occur anywhere in this gray region. So, even if we do have enough data, another advantage for process-guided deep learning models that we found is that we can, they actually perform quite well in unobserved scenarios. And so to test this, we created this artificial scenario where we're training a model, training the 3 different model types training 3 different model types on the on the spring and fall periods of a lake temperature time series. And then we're withholding all the summertime data, so the warmest periods of this lake temperature, and using that as the test period. So it's kind of like an unseen condition for the model. It's being trained on the colder periods and being tested on the warmer periods. And we expect, most models to not do very well because it's, unseen conditions. So we have the observations. So the observations closest to the surface of the water, surface of the lake, are going to be in yellow. About the middle of the lake is in green. The bottom of the lake is in purple. And then we show the performance during the test period for these 3 different models. So ProcessBased model is first. You can see it actually does a pretty good job of capturing surface temperature dynamics, even during these unseen periods during the summer. It might be a little bit faint, but the yellow line is matching the yellow observations quite closely. It doesn't do as well during the lower down on the lake. So the green line is kind of far off from the green observations, same with the purple line. And overall RMSE of 2.7 degrees centigrade. The deep learning model does quite well during the periods when it was trained on. So during the fall and spring periods, all the lines are matching the respective observations quite closely. But you can see during the test period of this summer where it has these unseen conditions, the yellow line just kind of flattens out. It doesn't really capture these dynamics of near surface temperature very well, and its overall RMSE of 2.3 degrees centigrade. But the process-guided deep learning model actually does decently well even in unseen conditions. So the yellow line is matching the observations pretty well. Same for the green line and the purple lines and all these conditions. So that's quite encouraging to us that even if we do have enough data for training a deep learning model, is it the right amount of data, and we can see, process-guided deep learning model can actually provide some added value in unseen conditions as well. Okay.
We have a question in the chat here.
Yep.
Is the RMSE given on test only or averaged also over train in the current slide with the new climates?
This is only on the test period. Yeah, sorry, I should have specified that. Okay, so now that was kind of the first half of the presentation. For the second half, I'm going to talk more about a very specific application of process-guided deep learning models that we're doing for forecasting stream temperature in the Delaware River Basin. So so we're generating stream temperature forecasts in the Delaware, and kind of also building a capacity for US Geological Survey for going from research to more operational forecasts. And first, I'm going to talk about why we need stream temperature forecasts. So there's this management plan in the Delaware River Basin called the Flexible Flow Management Plan. And it's designed to accommodate a variety of competing water demands. And it has 4 main objectives, one of which is protect fisheries in the tailwaters of the New York City reservoirs. So the New York City is right here, kind of off the river basin, but there are 3 different reservoirs towards the northern part of this river basin that are used to supply drinking water to New York City. But there's these competing demands for both human consumption of water, and then ecological value of the water. So maintaining cold water fisheries in the river basin is also important. So a large part of protecting these tailwater fisheries is the thermal habitat. So the upper Delaware is cold enough to support world-class trout fisheries and other important species in the basin. And water temperature targets are included in this management plan, with the primary target is to keep the Delaware River Basin at Lordville. So this red point right here, below 75 degrees Fahrenheit, which is 23.89 degrees Celsius. And to combat this warm temperature regimes, New York City reservoir operators are allocated what's called a thermal bank, which is a set volume of water that resets every year. And it's available to release when water temperatures at that red dot are expected to exceed this thermal threshold. So they're able to increase their release from the deep waters of the reservoirs, or this cold water layer of the reservoirs, to maintain these downstream temperatures. And the number of times the operator needs to make thermal releases is variable from year to year. You can see all the thermal releases in the last 3 years, 2019, 2020, and 2021, are a little bit varied. And especially in 2020, there's a lot of dates in which they had to make releases. It's a particularly warm year. And accurate water temperature forecasts with associated uncertainty enables reservoir managers to anticipate, warm periods and release the right amount of water from the reservoirs in order to mitigate these temperature exceedances.
We have a question in the chat.
Uh-huh.
Is there any difference between physics-informed learning and process-guided learning?
Yeah, that's a good question. Our group has kind of debated on what term to use for describing these models. And I know several other groups have decided to, or try to decide on what term to use. We have often used physics guided deep learning, or because oftentimes it's the physics that are actually guiding the deep learning models in our case. But we kind of stick with the term process guided because it's a little bit more encompassing of a bunch of different modeling scenarios. We're not always going to be using physics to guide the models. We might be using maybe some ecological theories or some other type of theories that aren't necessarily reliant purely on physics. And so there's not necessarily a difference between the two. I would say physics guided is a little bit more specific, and we try to use process guidance because it's a little bit more broad. Okay, so the objectives of this making temperature forecasts, we have these different modeling needs. First modeling need is that we need to accurately predict stream temperature dynamics, and we're using the process-guided deep learning models for this. And we also need this model to estimate and propagate prediction uncertainty into the forecasts. And we need a model that is able to ingest the most recent observations available so that it has the best starting point when making a new forecast on a given day. And so I'll briefly touch on this first one, and then also these second 2 points are kind of new to what I've talked about already in this presentation. So predicting water temperature below reservoirs is particularly difficult because reservoirs kind of decouple the stream temperature signal from the observed weather patterns due to these cold water reservoir releases. In this plot I'm showing you here, each line represents a site that is continuously monitored in the Delaware River Basin. The orange site, which is the warmest reach across this time period. It's kind of lower in the network, so towards the south part of the network. And the purple line is the cooler stream. It's in the northern part of the network, but it still has a pretty typical stream temperature dynamic that you would expect throughout the season. And then there's this goofy blue line, which has quite a different annual dynamic. It's one of the reaches that's below one of these reservoirs. And you can see that it has a kind of an unusual stream temperature pattern at the reservoir site, and it's a result of these reservoir processes. So, and also part of this decision making that humans are making when to release stream temperature or reservoir water downstream. So you can see during the middle of the summer, you would expect the stream temperature to increase, but because the managers are releasing water downstream, it actually maintains a pretty cool stream habitat in that segment. So, so our data science group has, found, and I've shown in previous slides, that adding process guidance to a modeling framework improves model accuracy for both lake temperature and stream temperature. This is an example of improving accuracy just for stream temperature. The orange line is the plain neural network for predicting stream temperature across a variety of data sparsity conditions. And we can see that every time we add some sort of process guidance, whether that is a temporal awareness with the LSTM, pre-training the LSTM on process-based model output, or adding some spatial awareness to the LSTM by including a graph recurrent neural network architecture, we increase the accuracy of this temperature prediction in streams. So for pre-training, we'd often train the deep learning model on stream temperature output, but as I showed earlier, these reservoirs in this stream network can produce some goofy stream temperature dynamics below these reservoirs. So for this case, we're actually combining two different process-based model outputs together to kind of give the deep learning model a better chance of learning about these dynamics across the entire network, whether that's below a reservoir or not. So if we look at our process-based model output that's using information from both a reservoir model and a stream temperature model, we can see that the process-based model predictions are improved compared to using the stream temperature model alone. The stream temperature model alone at this particular segment is given in the gray line. You can see that it's pretty far off from the black observations. But this new process-based model that we're pre-training the deep learning model on, so this blue line, has quite a bit better connection to the observations than just using the stream temperature model alone. So we're using this process-based model output to pre-train the deep learning model. And we're going to continue to use this process guide deep learning model to make predictions in the stream network. So next component that we have to do is to estimate model uncertainty when making the forecasts. And to estimate model uncertainty, we're using a technique called Monte Carlo dropout, where portions of the neural network are randomly removed during the training phase. And this technique is often a way to prevent model overfitting. But we're using the dropout during the prediction phase as well. And this gives an estimate of model uncertainty because there's slight variation of the model that are being used to make a prediction, with each of the ensembles of the Monte Carlo dropout prediction. In addition to this Monte Carlo dropout technique, we're also using uncertainty in the drivers of the model. So we're primarily using weather forecasts to drive these deep learning models. And the National Oceanic and Atmospheric Administration has this global ensemble forecast system, which has 31 different weather forecast ensembles, and we're making actually a total of 3,100 ensemble predictions for each stream segment each day using the combination of these weather ensembles and the Monte Carlo dropout technique. So now that we have, some uncertainty associated with the model, how do we give the model best starting position to make a forecast every day? So with that, we're using a data assimilation technique along with a deep learning model. So every day when we're making a prediction of stream temperature with associated uncertainty, there are also observations that are being collected along the stream network. And we want to use data assimilation technique to adjust the deep learning model states to ensure that the next day's prediction are starting from a good place. So specifically, we assimilate observations into the model. We're updating the temperature predictions and the cell states of the LSTM with a technique called the ensemble Kalman filter. It's a pretty common data assimilation technique, especially in process-based models. And this is adjusting for any errors in the model and improves the predictions at the next time step. Specifically, if we dig into like what this looks like in an LSTM, this is just a very simple schematic of a LSTM where we have hidden states and cell states, some drivers in green at time step t. Given these drivers and the current states and weights, it produces a temperature prediction at this time step. We can compare it to the observation and using the ensemble Kalman filter, adjust the temperature predictions and also adjust the hidden states and or cell states of the LSTM. And then these adjusted states get used to make predictions at the next time step. Okay, I'm also going to briefly touch on like how do we turn this into an operational forecast. So we now have a model that can make predictions with associated uncertainty using the most recent data available. But for our operational needs, we need to produce a daily updating 7-day forecast using the most recent meteorological and observation data. And we also have this deadline to deliver these forecasts to the New York City reservoir operators by mid-morning every day. So they need to make a decision every day about releasing water tomorrow or a few days in the future, and we need this to be delivered to them at a timely fashion. So this is a brief overview of our workflow. Every day we're automatically downloading the most recent weather forecast from NOAA starting at midnight. It takes about 4 hours to download, and it takes quite a long time because we're also creating an archive across the entire US so to use in other model prediction applications. Next, we automatically download the most recent stream temperature observations and reservoir releases. That's triggered at about 9 a.m. every morning. And then we assimilate these observations into our model. We then use these data to generate forecasts with our model, which happens around about 9:30 a.m. every morning. And these forecasts are archived and then summarized and then sent to a bunch of different places, including the reservoir operators, but also a public website so that anyone interested in seeing what the stream temperature forecasts are for that day can visit that website and see what's happening. So I'm going to jump into some of the model evaluation that we've done and just a brief overview of the terminology that I'll use. So I'll often be saying lead time, and lead time refers to how many days in the future that we're making a forecast prediction. So when we're issuing a forecast, for example, on August 1, the same day forecast often has a lead time of day 0. And then any day in the future has an increasing numeric value. So August 2 predictions would be a lead day of 1, and et cetera, et cetera. So just a quick overview of terminology. So, if we zoom out to the entire forecast season, so this is from last year, the 2021 season, we can see that our deep learning model does a decent job of capturing temperature dynamics. And this is at a 1-day lead time. So predictions for tomorrow across the entire season. The 90% confidence intervals are the gray band across this entire plot. And then the white line that's in the middle of that 90% CI is the mean of all the ensemble predictions that we're making. The observations of stream temperature that fall within that 90% CI are the black circles. And the ones that fall outside the bounds are in the open circles. So most of the observations fall within this 90% confidence interval, which is what we would want. In fact, about 79%, which is, we're a little bit overconfident in our model, but I'll talk about ways that we're trying to improve that. We have a fairly low root mean squared error, about just over 1 degree C. and a quite low bias, so near zero bias for this model. In this site in particular, this Lordville site, this is the one where the managers need to make a decision about releasing water. So this site has a thermal threshold that they need to stay below. So this site in particular is important to produce accurate and consistent forecasts. If we summarize this model accuracy across all the forecasts that we made and across all lead times, we can see that, again, the model has about a 1 degree C RMSE at a 1-day lead time. But this accuracy decreases the further out we forecast, but only about to 1.6 degrees C at 7 days out. And in this plot, we're comparing 3 different forecasts that we had produced. One is the deep learning model without a data assimilation. So this is the orange line. One is the deep learning model with data assimilation. So it's the blue line. And then there's another forecast that we were using, which is kind of a benchmark. It's called the persistence forecast. And that just predicts the next 7 days to be the same water temperature as today. And so this is kind of a very simple forecast. And the hope is that your model can do better than this persistent forecast. And it does, which is good. If it's not doing better, then you should kind of reevaluate your model that you're producing. The model with data assimilation marginally improved forecast accuracy, but this is mostly at day 0 and day 1 lead times. We think this is likely because both models, so the one with and the one without data assimilation, had access to the same information. So they both had access to recent observations. But the data assimilation algorithm only marginally improves the model because it makes use of this information a little bit differently. By it's adjusting the LSTM states, whereas the deep learning model without data assimilation is not adjusting those states. We're particularly interested in 5 different segments across the stream network. And if we look at across all these 5 stream segments, we can see that the deep learning models all perform better than the persistence model, which is good. And they're all below 2 degrees C RMSE at 7 days out, which is also pretty good. And we can see that the data assimilation algorithm improved the forecasts marginally at all sites. The biggest improvement was at this middle site, so this Bridgeville site. But all the other sites were, again, kind of marginal, and most improved at day 0 to day 1 lead times. So I'm going to zoom into one particular time period during the year where there were actual thermal exceedances at this Lordville segment. So on June 29 and June 30th, there was these 2 days actually exceeded this thermal threshold of 23.89 degrees C. So that horizontal line there. And we can examine how well our deep learning model with data assimilation was performing around these days. So all these plots are their 1-day lead time. So tomorrow's forecast across all these days. Each point on here that isn't an observation are the different ensemble model predictions. So each day has 3,100 ensemble predictions. And then we can color code these by whether they're predicting an exceedance of this threshold or a decedence of the threshold, so above or below that thermal threshold. And we can also color code them by whether it's a false decedence or a false exceedance, or a true or true decedence or true exceedance. So we would hope that the model would be in gray. So true exceedance is the darker gray, true decedence is the lighter gray. The model is predicting a little bit colder than expected if it's in blue, and then false exceedance is in the more salmon color. And at the very top here, we have the probability of that day exceeding this thermal threshold. And this is a metric that the managers reservoir operators were using to decide on whether or not to release water. And we can see that like the days around these exceedances had a much lower probability of exceeding that threshold, and the days that it did, it was predicting about a 26% increase or a 32%, 32% chance of increasing or exceeding that thermal threshold. Sorry. And we can see also how the model predicted these thermal exceedances across all lead times. So we can see that more prediction instances were true thermal exceedances, or this dark gray points at the shorter lead times, so the 0 to 2 day lead times, compared to the longer lead times. So the model wasn't doing a very good job of predicting true exceedances at like 5 to 7 day lead times. These longer lead times, although not as accurate as the shorter lead times, were still useful for the reservoir managers, especially for staffing coverage around the weekends and holidays. They found it particularly useful. Then we can also compare, so the prediction of these true exceedances from this deep learning model with data assimilation to the deep learning model without data assimilation. And we can see that the data assimilation technique actually helped the model predict more true exceedances. So this y-axis here is the deep learning model with data assimilation minus deep learning model without data assimilation for these prediction instances. We can see that the positive value means that there are more true exceedances with the data assimilation technique included, which is indicating that the data assimilation algorithm is helping improve the deep learning model forecast accuracy around these thermal thresholds. We also want to evaluate how well we're characterizing uncertainty, and we can do that by creating these reliability plots. So if we look at the entire forecast period, our model was slightly overconfident in our model predictions, which I was indicating a little bit earlier. Our hope is that these colored lines would fit along this one-to-one line, this diagonal one line here. And that would indicate that our model is characterizing uncertainty perfectly, because that would be 10% of the observations falling in 10% of the confidence intervals and 90% of the observations falling in 90% of the confidence intervals. But however, about only 80% of the observations were falling in the 90% confidence intervals, which indicating that our model is slightly overconfident. And we need to expand these bounds of uncertainty a little bit to make our forecast a little bit more reliable. So that was just for one site, but it was true for all the sites, all these 5 sites that we were interested in. They're all slightly overconfident. As you can see that they're below that one-to-one line. So this year, we're moving towards implementing a different way to characterize uncertainty with these deep learning models. And we're moving towards this method called mixture density networks to improve our forecast uncertainty. So mixture density networks can predict the mean and variance of a distribution along with the weights for different distributions if you want to include a bunch of different distributions. And this isn't as opposed to we're just making point prediction in our previous method. This is predicting actual distribution, and then we use the negative log likelihood to as our loss function for during the training procedure. So this figure just kind of is a simple schematic of what this mixture density network looks like. This is an example of predicting 3 different Gaussian distributions, and then combining them with the weights for those distributions to create a final prediction distribution of the temperature. And again, you know, even if you have the same mean and variance for these 3 different distributions, there's also another parameter for the weights. So how do you combine these different distributions? And this example is just showing if you weight the blue distribution more, you get a distribution like this. If you weight the salmon distribution more, you get a distribution like this. So kind of a precursor to using these mixture density networks. So far, it looks like this new implementation is looking promising for improving our model forecast reliability. this reliability plot, it looks like these lines are falling a lot more closely to the one-to-one line, as before they were a little bit more overconfident. Now they're kind of, right along this one-to-one line, which is encouraging. And finally, I think, for moving the US Geological Survey from research to operations, I think there's a lot of value in moving our research products to more operational products. And this is kind of indicated by the feedback that we've been getting from the reservoir managers. So they told us that it's likely the addition of the USGS forecasting product improves their skill and confidence at forecasting stream temperatures. Like I said earlier, the 7-day forecast actually helped them with staffing coverage around weekends and holidays. And they, our primary stakeholder was this reservoir manager, but they also said that they see additional benefits for anglers and other ecotourists in the basin when it is public. So that's encouraging and good motivation to create a little bit more operational products. And then finally, there's some model improvements that we want to include with the stream temperature forecast, and then I'm just kind of highlighting them here. We want to fine tune on some archives that we've recently downloaded from NOAA. We want to include a little bit more spatial awareness with this model. Last season, we were just using the temporal awareness or the LSTM. And like I mentioned earlier, improving uncertainty quantification using these mixture density networks. Yeah, and that's kind of the presentation that I had. I would take any questions if there are any.
Thank you, Jake.
Yeah.
Do we have any questions?
Can we ask questions here, or do we have to write them in chat?
No, you can ask them directly.
Yeah, thank you. It was very interesting presentation.
Feel free to turn on your camera.
Oh yes, sorry, of course. Let's see. I'm not sure if it worked. Did it work?
It works.
Yep.
Yeah. I was wondering about the performance of the models that you shared some graphs. So on the y-axis you had the performance, and on the x-axis you have the number of data points.
Mm-hmm. So like a.
It was in the more or less in the beginning of the.
Sorry. Like this graph?
Yeah, like this, for example. So I was wondering, how does the training period length compare to the validation or the performance training length? Or is 980 points all you have, or is it 980 points for training and 980 points for validation?
Yeah, it was roughly split in half. So there were roughly 980 for training and testing, but we use the same test period for all the data sparsity conditions on this plot. So I think there's about 980 test days and up to 980 days of training. So does that help?
Mm-hmm. So that's great. And oh, sorry.
I was going to say, this is one of the most well studied or well monitored lakes that we have. So there aren't too many other lakes that have more than 1,000 observations you can use.
And it's very interesting that it actually flattens out to around 1. But what does 1 mean? Like what performance would it be in percentage? Like you said, is it like 70%, 80, 90?
That's a good question. I'm not sure if I know off the top of my head, but in terms of, it's kind of like unparalleled performance for predicting lake temperature.
Mm.
It's quite good. There are some other lakes that you can predict below 1 degree C, RMSE, but they just have a little bit more simpler temperature dynamics in those lakes. And sorry, to be honest, I don't know what the, like an R squared or something would be of this, but it'd be quite good.
Right, thanks. I don't know, maybe someone else wants to ask questions also. I have a couple of more.
Farouk has raised his hand. Do you have a question related to this? Otherwise, perhaps I'll squeeze in a small one related to this. So you talked together with this, you talked about these 3 different regimes, and sort of the last regime. Do you sort of think that that's obtainable, and sort of when will it come? And have you seen this 3rd regime where the basic deep learning without the process guiding outperforms everything else?
So we've always, well, I think almost always have seen process guided deep learning outperform a pure deep learning model. But we have also been working in systems that have pretty good theory. So we know a lot about how stream and lake temperature responds to climate and responds to weather. And so we can do, pretty good job of adding in, custom loss functions or pre-training on process-based model output that we're quite confident in those outputs. So I think for the systems that we've been working in, we haven't encountered this 3rd scenario. But I think, maybe going into maybe some ecological systems or some other systems that don't have as good of theory that we can rely on, we might just rely on the data that are available. And I wouldn't be surprised if deep learning model is better.
But it also would require other amounts of data.
Yep. Yeah. It's true. And then there's some of our colleagues would, swear by the deep learning model always performing better too, because we're telling it things that are simplifications of the real world, whereas we shouldn't be telling the model that itself. It should totally just rely on learning the relationship between input and output and figuring that out for itself. But yeah, you would need a lot more data. And, with the systems that we've been working in so far, we haven't encountered this 3rd regime, but I don't know. I wouldn't be surprised if we get there at some point.
Okay, thank you. Farouk is the next.
Thanks for a good talk. I have a question. What do you really mean by process guided? Because it means different things in different domains. And like one of the questions asked about the difference between physics informed versus process guided. I'm wondering, what do you really mean? Is it a set of differential equations or heuristic algebraic equations? And the second thing I wanted to ask about, you talk about forecasting. So there is the question of accuracy, but there is also a common problem with forecasting, and that is error accumulation. Like most algorithms have this issue that errors just keep getting bigger. So did you encounter that, and how did you deal with it?
Yeah, so for the second question, you mean error the further out that we're forecasting? Yeah. Yeah, so for that one, yes, we did expect error to accumulate, and that was shown in the forecasts that were further out. So our 1-day forecast we were a lot more confident in. Our 7-day forecast we were less confident in, and our confidence bounds were I don't know, maybe twice as large as the 1-day forecast, and that's to be expected. We hadn't tried forecasting further out than that, and I guess we would expect the errors to increase even further than that. But that's expected, and we hope that the error would increase a little bit because you know, we are less certain about those time periods. I don't know if that answers your second question, but.
Well, thank you. I think it does because I was wondering if process-guided models help to get rid of that problem. So yes, it does help answer that question. Thank you.
Yeah, we haven't, I guess we haven't compared it to like maybe like a process-based model that's making a same forecast at the same time, but that would be a good comparison to do to see, like, you know, how is the uncertainty changing between those two different models. We do have a, well, so when moving to this mixture density network technique for predicting uncertainty, we're using some explainable AI techniques to also see which input features, or so which meteorological drivers are contributing most to the, like the standard deviation or the variance of those distributions. And so I think that's going to be very valuable for digging into like your question a little bit more. So we'll be able to say like, okay, temperature is contributing most to the standard deviation component at day 1 or day 3 or day 7 or whatever, like something like that. We haven't done that analysis yet, but it's possible with these mixture density networks. And then for your first question, process guidance, we are saying that process guidance is happening when we're pre-training the model on process-based model output. We are also including custom loss functions that penalize the model for violating the law of conservation of energy. So we actually encode the law of conservation of energy based on meteorological drivers and the energy in the system, the internal energy of the system. And then if the model is going to predict tomorrow to like magically create some energy or destroy energy, we will penalize the model for violating that. And then so that's one of the process guidance that we're using. We have some colleagues that are also including differential equations into the model itself, but that's not, I wasn't presenting on any of that here, but that's also another process guidance that we're using. And in terms of, you know, the difference between physics guided or process guided, I would say most of the stuff that I showed here is considered physics guided, but we generally use the term process guided because it's a little bit more open to a bunch of different systems.
Thank you.
Yeah, thank you.
Next hand raised is Alexis.
Hi, can you hear me?
Yep.
Great, thanks for a good presentation. So my first question is about, essentially this slide is quite good because I'm asking about the fact that I guess data here means annotated data. And there's also a big trend in artificial intelligence, computer vision, and so on to do sort of self-supervision where you don't rely on so much annotated data. So I was just wondering if you are aware of if there's efforts at sort of combining process-guided learning and these sort of self-supervision techniques, because both of them can lead to less dependence on data annotation.
Yeah, good question. To be honest, I'm not aware.
Yes.
But I wouldn't be surprised. And we do have a colleague that recently put out a review paper of process guidance or theory guided or physics guided, whatever you want to call it,
yeah.
Machine learning. And I can share that. I think it's still a preprint right now, but
yeah.
They reviewed kind of the field and you know, have several hundred references, so it might be something to dig into.
Yeah, because I think it would be interesting to have sort of some sort of comparison where you have like pure deep learning models,
Mhm.
but which are also allowed to be sort of trained in some self-supervised way, because then you could also see if it really helps with the physics part, if you also do the pre-training, and or if combining them is sort of even better. And another question I have is, as you include more and more sort of process guidance, would you say that this affects the model design of your deep learning model? For example, the size of the model. An example could be that if you have more process guidance, then maybe you would need a smaller deep learning model or something like that. Do you have any comments on this?
Yeah, that's a good question. We have been kind of running into some computational limits from what we have been using. So like, yeah, straight LSTM is a lot easier to work with. And now that we're scaling up to larger regions, using a recurrent graph convolutional network has been a lot more computational demanding. And we have been thinking about how to split up these models. Can we model the entire network, or do we model just like separate portions of the network at a time? And so, yeah, it is more computationally demanding. If we want to model something like continental scales, we're definitely going to have to figure out some other techniques or split up the model in a different way.
Yeah,
so, yeah, that's a good question.
Thanks again.
Yeah, thank you.
Thank you very much, especially Jake, for this nice presentation. Next week, we have a presentation by Professor Thomas Schön from Uppsala University. He's going to talk about formulating flexible probabilistic models. So the same time next week and the same link. Thank you for today.
Thank you very much.
Bye-bye.
Bye.
Bye.